Hello, everyone. I'm Spyros. I'm from the CERN Cloud team, and I will talk to you about the latest developments that we have for container use cases. I will start. This is OpenInfra. It used to be OpenStack Days. I will start with an OpenStack project, which I used to be the project team lead. It's the OpenStack Magnum project. I will go very quickly what it is because it's like a few years that it's out. Some of you might know what it is. It's a very simple and small OpenStack API service that creates Kubernetes clusters on demand. It's just a very thin layer over other OpenStack components. So it leverages Keystone credentials, and you select what kind of cluster do you want, and all the components of the cluster are in the same tenant. It has some advanced features like multi-master, load balancing for multi-masters, select different options bit for networking, and so on. It supports these container orchestrators, but as you can see, previously when I had these slides, all logos had the same size. Now, obviously, Kubernetes is a bit bigger because you will see later, based on the number of the clusters, at least that we have in our cloud, it's clearly the biggest winner in container orchestrators. And based on the feedback that we have from the OpenStack upstream community, there are a couple of contributors that contribute exclusively for Kubernetes in the project. So what is a Magnum cluster that it's offered as a service? A cluster is composed by a few OpenStack objects like compute instances, which are either the VMs or physical instances, virtual networks, which are created by Neutron, the networking component of OpenStack, security groups similar to AWS, block storage volumes, which is provided by the Cinder service, and other resources like load balancers, which are created for the API of the cluster or for services that Kubernetes exposes. All this orchestration is done by OpenStack Kit, which is a tool to write templates like CloudFormation, and you can define how your cluster want to look like, and you just give it to this API and creates it. So Magnum maintains a set of templates that we use to create the clusters. What runs on the clusters now, and what Magnum actually does, apart from creating this, all the resources. It manages the life cycle. It means that you can scale up or down the cluster. Recently, we added also autoscale the cluster and upgrade the clusters. That means that we run the component that all other cloud providers have, which is the cluster autoscaler, and scales up and down according to the needs of the workloads. And we can also upgrade with an API command to the next Kubernetes release, or just to upgrade Docker, or just to upgrade the operating system of the compute instances. What we also added in the last release was node healing, which means that if a node is marked as not ready in Kubernetes, at least, which is the main use case, the node is just replaced automatically. This is like a beta feature, but we're still working on it. It kind of works for now. Also, what we try to provide is like self-contained monitoring and data store for like etcd for the Kubernetes cluster, or even for Swarm, and additional resources like webhooks that I will explain later, and so on. I will skip this slide. This is mostly for developer conferences, but this highlights that on both sides it's the user. From the right, it creates the cluster, and when the cluster creation is done and Magnum did all the orchestration, then the user can talk to the cluster using the native API, which is kubectl or kubectl or Docker. And for measures that we used to support, or we kind of support still, just the REST API without a client. So how does the workflow look from the point of view of the user? We advertise some cluster templates that we have. For example, we have Swarm HA, Kubernetes HA, and so on. The user just selects the cluster that they want, and with one command, they create the cluster. For example, in this case, We create a Kubernetes cluster with 100 nodes. We just give it a name and the node count, and a few minutes later, the cluster is created. Then the kind of magic is to retrieve the credentials of the cluster. This could be either TLS certificates or Keystone Authentication that I will explain right after, which is like the new way to authenticate with a cluster. And then you just use kube control or Docker. Why we use Magnum and why would someone use, and who it's aimed for? If you're an end user and you have a small data center, probably it's not for you. It's mostly targeted to big data centers or to teams that want to provide clusters to other teams. In our case, we're like a public cloud provider for the high energy physics community, and you have 3,000 to 4,000 very active users, but if we extend them, it could be like 13,000 users. These resources are kind of free for them, but they must go through their supervisors and so on to ask resources from us, and then for us to provide them to them. And we leverage OpenStack to do all the accounting, and it's like a very easy entry point for new users. Someone doesn't have to know how to deploy or configure Kubernetes or even Docker. It can just ask the service for a cluster. It will receive an endpoint, and then the user can start developing an application or just do some analysis. A few things that we considered and other operators need to consider is Magnum has a lot of options regarding networking. So the operators must select carefully the features that they want to advertise. For example, by default, the service creates a private network per cluster and a floating IP per node. In a public cloud, this can be very expensive because floating IPs usually are public IPv4s and they're very expensive. And another option is to select multi-master or single master. If you want some opportunistic workloads to run, you don't need many masters, and you don't need an extra load balancer and to pay resources for it. Another very important part for us that allowed us to create the service was that we run a container registry. For us, it is run by GitLab, but it's like crucial for a container service to function, to have a local registry, because then all the time and bandwidth and computing resources are wasted pulling containers from Docker Hub and elsewhere. Also, one thing is very important for security is to rebuild all containers. Don't just rely on containers outside, because when we provide the clusters to the users, we essentially provide them software. So we must be sure where it comes from. I will talk about some upstream features which we developed at CERN, but we contribute them like immediately in the upstream community. So first, features get merged upstream, and then we consume them downstream. The first one was like an internal feature that, not exactly internal, it's like a refactoring of an existing functionality, which is to resize the cluster. We deprecated an old command. So what it's important for existing Magnum users is now that they can select which nodes they want to remove, because this was left to the service to decide it, like a bit smart to select which nodes didn't have a lot of containers and shut this node down, but now the users can specify the node. It's merged in a stable branch and also in the branch that we cut, and it will be released in the middle of April. This is how it looks like. Actually, this is very similar the CLI that we checked in GKE. So you just do OpenStack cluster resize. You pass the group of the nodes. For example, this is the kube worker node group. You pass the name of the cluster and the number of nodes, and it scales accordingly, up or down, depending on what was the previous count. And at the bottom, we have an example that the user tries to remove a specific node, so it passes the UUID of the server the user wants to remove. And this is a very big feature that we added, and if you get an OpenStack Cloud right, it gives you a lot of possibilities, which was to actually add node groups, because when we started to do the project, we had the two default node groups, one for the control plane and one for the worker plane for the cluster. So now we have the option to have many groups, either for control plane or a data plane. In this example, we have a master node group that has 3 masters for HA, and then we spread the workers in different availability zones. For example, we have a flavor in one availability zone and the same flavor in the other availability zone, but also we have a physical machine added to the cluster, plus some VMs that have GPUs. That wasn't the case before. Before, you could only create VMs with GPUs, and that's it, or only physical workers. Now it's possible to have heterogeneous clusters and scheduled workers, scheduled workloads inside the cluster, as the user or the team pleases. This is how it looks like, the API. You can list the groups. Now you can see that you have the masters and the workers. Before, it was like one single API object in the service. Now it's separated too, and you can inspect. And adding and deleting and scaling groups, I haven't put them because they were just merged last week. So I didn't want to rush. What I found very interesting that we implemented the last cycle was authentication with Keystone. This is what was described by, what was the company? Research, the fintech talk, I don't remember the name, sorry. And that implemented the same way to authenticate instead of using TLS certificates to authenticate with Active Directory. It happens that we also have Active Directory, and we had the same use case, because if you have a cluster that is operated and the authentication is done with TLS certificates, if a user creates the credential for the cluster, then even if you delete from the organization the user's credentials, the user can still access the cluster because it uses this TLS, the artifact for the cluster. Using Keystone authentication and integrating with central account management of the organization, in our case, is LDAP with Active Directory. We can use Kerberos to authenticate with OpenStack, retrieve a token, and based on that token, and be sure for the identity of the user, and then check in which groups the user belongs. And this is the workflow. The user creates the cluster with a specific label defined, but this is also on by default. Then exports a token, similar to the kubectl login command that was described in the previous talk, and then talk to the Kubernetes API. The next very big feature that we added the last cycle was autoscaling. AWS, Google, GKE, and AKS have their own autoscalers. Also, Alibaba has its own. So we added one for Magnum, which essentially consumes this resize API based on all the simulation that the cluster autoscaler does. It's very interesting to go to the pull request. It's like one of the top, by far, the pull request with the most comments, like over 100 comments. The discussion was very interesting, but the maintainers of the autoscaler were very supportive, and in the end, we finally merged a first iteration of the autoscaler, which will be released in the version 1.14.1. It's not in 1.14.0 yet. Another feature that we added was cluster metrics. As I said, we have internally a monitoring system. We used to have only for log collection. Now we also add for metrics based on Prometheus, which are collected by the metric server, which is the new internal component for metrics for Kubernetes, and directly from the kubelet. I will rush a bit because I want to really go to the use cases of CERN, which are most impressive, I think, because more or less you know all these things already. Very quickly, for upgrades, we're merging this in the coming weeks, in the next 2 weeks, because after it's the release, we will support 2 modes of upgrades. One is in place without any downtime of the nodes, and the next, the other mode will be with node replacement, similar to what the Google Kubernetes engine does. So one by one or batch by batch, the nodes will be replaced and new nodes will be enrolled, and Kubernetes will schedule the workload accordingly. No further compatibility means that for all clusters this operation will not be supported, but we will try to help operators to alleviate that. More add-ons include pod security policy, which was very interesting because I just saw it in the talked just before, and we started implementing it like 2 weeks ago. And we also support 2 ingress controllers. One is Traffic, which is widely known in the container world. The other one is Octavia, which is OpenStack specific and works only for Octavia-enabled deployments. Also, node problem detector is a very standard tool in Kubernetes to check the health status of the node. And it can be customizable. For example, if you have a special storage plugin, it can check the health status of that plugin. Final releasing for the CERN container service. As you imagine, it's based on OpenStack Magnum. This is one of the most impressive slides that we usually have in our presentations. We started in 2013. At the moment, we have almost 300,000 cores, and we run 34,000 VMs. For Kubernetes nodes, not exactly Kubernetes, but for container cluster nodes, we have almost 1,000 to 1,800. 1,600 roughly is Kubernetes, but they are steadily grow. And we have like around 500 clusters. Some of them are very small. It's mostly for developers to experiment with Kubernetes, and instead of having a Minikube or something else in their nodes, they can have a running cluster in our cloud and create as they want on demand without consuming resources on their laptops. This is how it looks like for the numbers that we have. We have 525. This number fluctuates a bit because we have a probe service that checks that the service works. So it might be 540 if I check now. And we have the number of nodes that I mentioned. And if you check the number of clusters that we have, measures are around 10. And the dominating number is Kubernetes, which is like 3 times more than Swarm. And for the Swarm use case, it's mostly one user that we have in the cloud that uses many, many clusters. We use the latest stable release of Magnum with some custom patches that we add because we have a very special network, and for the integration that we did with Active Directory that we have in our data center. Also, we have added a dedicated like CERN-specific log collection plugin, which is based on Fluentd, to push to our central Elasticsearch with a special mechanism that we have deployed. One of the most challenging parts for running Kubernetes was storage. For storage, we have 4 components. 2 are very well connected, which is the CSI, the Container Storage Interface for CFFS, which is a shared file system backed by Ceph, and the Manila external provisioner. Manila is the service of OpenStack that creates shares in shared file systems like Ceph, Gluster, or NFS. In our case, it supports only CFFS, and users can create claims, and this external provisioner will just carve shares in CFFS for them and mount them in the cluster. I have a link to a very impressive blogspot that my colleagues did with some results with 10,000 clients connecting to the same share. So it proves that Ceph actually really scales. And then we pass to the 2 very CERN-specific storage solutions. One is the CVMFS, which is the CERN VM file system. The CERN VM file system, it's exclusively used to distribute software. So the experiments around the world push in a central place software, and then with a hierarchical layer of squid caches, it distributes across the different data centers, and in the CERN data center as well, which is like the top-level data center. Then we have EOS, which is a CERN-specific open source, of course, file system, which stores the actual physics data. This is not a CSI plugin yet, but we're working to make it standard, although I think we are the only users of EOS. But what are physics data? This slide came a bit late, but quickly, if you don't know, CERN is the biggest particle physics laboratory in the world. It runs the LHC, which creates 2 stable beams that collide in 4 points in the accelerator ring, and they create a lot of data. When I say a lot of data, it's many gigabytes per second, and every year we store around 70 petabytes, and all this data need to be analyzed, and we run a very big batch farm for that. This is one of the biggest use cases, and then some other end-user analysis for physicists and some emerging machine learning technologies. The next use case is, again, of course, data analysis of physics data, but with a more modern tool instead of a batch farm, which is the Apache Spark. And that we have a working an analytics group that they start working on it, and they work closely with the upstream community to use the Spark operator, which runs exclusively on Kubernetes and manage the whole life cycle of the Spark deployment. Two more use cases. Sorry, I'm a bit rushing because I'm almost out of time. This is one very promising one that it might not replace, but it's very close to a batch farm. It's a workflow engine built on top of Kubernetes. It uses only Kubernetes jobs, not CRDs, just the batch jobs of Kubernetes, and creates complicated workflows that can be in some levels parallelized or not, if the algorithm allows it, and it can analyze a lot of data very fast. The very powerful part of this is that this can be deployed in any cloud that runs Kubernetes, because like Kubernetes is the standard API, and either in Google Cloud or AKS in Azure, it's the same API, or in our cloud in OpenStack, it's exactly the same, and users can deploy it and do analysis without having to refactor their application. And the two last use cases are the batch use case that I mentioned, which is based on HT Condor, which is like a very old tool, which we try to experiment of deploying Condor in Kubernetes, not consuming the Kubernetes API, but just managing Condor with Kubernetes for better monitoring and easier handling of the deployment, using Helm and building our own infrastructure around it with the container registry that we have and an in-house Helm repository. This use case is an extension of running Condor on Kubernetes, which is federating a lot of clouds. In this example that you can see in last year's KubeCon Europe that my colleagues did, they federated, I think, 7 public clouds, and they ran one single batch farm which was controlled centrally at CERN and was extended as we wanted in the public clouds. In this year's KubeCon, I don't have the link, but I want to upload the slides. I will put the link. They have another use case, another demo that will do the same thing, but will also autoscale. They will autoscale inside our cloud and in the public clouds as well. This one is a very internal component, which is managing the secretariat and administrative tasks at CERN. But what's very, at least amusing to me, is that they run on Kubernetes some Oracle databases and some Oracle WebLogic applications to manage our internal e-document system, and I think very soon the salaries, so I hope this works very well. But they distribute in many Kubernetes clusters for a high availability, also for the high availability of the control plane of the clusters, because if you have a cluster spread across availability zones, the etcd data store, which is the heart of Kubernetes, might suffer from outages, and it's better to spread in different clusters to have complete HA for the data stores. In conclusion, sorry that I did very fast, but a lot of people ask us why we have so many clusters. The reason is that we have many diverse users with very diverse workloads. For example, the batch farm cannot coexist in the same cluster as the administrative clusters, or the Spark, which is very network intensive and compute intensive. It will exhaust the resources for the batch farm. That's why we have many different clusters for different use cases. And the last note was that Kubernetes won the developers. Initially, it started, Swarm was the most popular one because it was much easier for users to understand. But when they went to day 2, as we say in containers, they saw that Kubernetes provides a lot more features and that they could design more better applications with much more sophisticated architectures. And this is some notes that are for OpenStack developers if you want to involve in Magnum. And you can hit me on Freenode and IRC because we are a very traditional project, or in the mailing list of OpenStack. And that's it.